Okay, so we start my second lecture on computer simulations of glass-forming liquids. So I've prepared a summary of the first lecture. I've noticed that all the students are very precise and taking notes. At the back, I'm not too sure about the lecturers, what they were doing. And I know that Mark Ediger wasn't there, so this summary will be useful for you and probably for Lisa Manning, who told me kindly this morning at the breakfast that she was working during my lecture. So that's also for you, Lisa. Okay, so the summary of the first lecture was I started by explaining why it was maybe interesting to do computer simulations of glass-forming liquids, and it was a way to interpolate between experiments that are sometimes complex and theory that are hard to do in finite dimensions and live sometimes in a different world. So we make the connection between the three types of approaches. Then I introduced a number of simple models, and I argued that we now had good models for glass-forming liquids, and I challenged Mark to tell me why they were not so good. Then I explained how it worked to do computer simulation, that the basic outcome was a time series for the positions of all the particles in the box, and that's it. And that's how you have to compare the outcome of your simulations to experiments. So I said, let's construct the density field, the pair correlation function, the static structure factor. I told you what was the information inside. Then we went to thermodynamic quantities, energies, for instance, pressure. Then we went to time correlation function, microscopic response function like the isothermal compressibility. From time correlation functions, we got relaxation times that we could compare to experiments, up to the viscosity, say, through Green-Kubo types of relationships. So just by watching the movie of the particles in the box, you could reconstruct the viscosity and then compare to the experimental data that Gilles has shown during his first lecture. Online, if you go to the program of the conference, there is an exercise, and the exercise is about deriving the expression for the viscosity from the particle positions and velocities. So together with Leo, we decided not to print and copy this exercise on paper just to save some trees, but I encourage you to do the exercise. It's on the web page. You can download the questions. It's an exercise about deriving Green-Kubo relationships. And again, just as Giulio, I'm here to try and help you doing the exercise if you want. It's about deriving the viscosity. Then I went into a historical summary of computer simulations. And the outcome of this was that over the last, say, 30 years of computer simulations, if you watch the time window that people are able to simulate, then the increase in terms of how many decades of relaxation time can you obtain in the computer simulation was about 2 to 3 decades, 3 orders of magnitude. And Gilles told you that the gap between computer simulations and typical experiments, it's about 8 orders of magnitude. So at this pace, it means that we would need to wait until 80 years later, we'll be able to catch up with Mark's experiments on molecular liquids at the glass transition. So today it will be about closing this gap. That will be one important part of the lecture. Finally, I introduced the idea of molecular dynamics, which was so basic that it was just solving Newton's equation. And then we discussed discretization, neighbor list, all these details that you can find in textbooks. Okay? Then I mentioned that if you don't want to learn molecular dynamics, you just download this LAMPS software. So you all laughed, I remember, but it's not funny. The thing about LAMPS, I think it's true, it's a black box. It's very easy. You just have to understand how to set up the temperature and everything, and then you get results automatically, I would say. So it means that in principle you don't have to write your own code. I would not recommend that. It's probably best to learn the molecular dynamics. It's so easy that you can write your code, learn how to do the things, and when you're very efficient at your code, then you can move up to LAMPS if you want to do something different that LAMPS has already done for you. But don't go to LAMPS directly, I would say. Okay, so we ended up with a question by Guillaume, who asked about, in Newton's equation, energy is conserved and the temperature essentially follows from the microcanonical distribution. And I answered that, there are many, many different types of thermostats that exist in the literature. You can take whatever you want, you thermalize with this thermostat, and then you do your microcanonical simulations where the dynamics is pure and simple. Okay, so I had prepared a note about some of these thermostats, but I think I will skip this demonstration for today. So at the end of the historical summary, I showed you this plot, and so today we'll come back again to this plot, so that's why I show it again. So it's a plot of configuration and entropy measured in the hard sphere system as a function of the inverse of the pressure, which you can think of as the temperature if you want. And so today what we'll try to achieve is how to compute this blue curve here, which is the simplest estimate you can think of about the configurational entropy, which is taking the total entropy and subtracting something which is akin to a vibrational contribution to the entropy, as Gilles and Giulio have explained before. And as I told you, this is the mode coupling transition. This is where typical computer simulations typically stop. Okay, and so what also we learned today is how to extend these simulations to the experimental glass transition marked as a blue box here and below that temperature. So these are the goals. Thanks. So this is the program for today. So we'll take a look at this curve. So maybe something you should notice. So this is the steep decrease of the configurational entropy as you decrease the temperature. Visually, if you try to extrapolate this guy, you'll find that it seems to vanish at some finite temperature. So it suggests something like an underlying phase transition. Something which may be important in the talk is the type of order of magnitude that you get. So in our rescale units, in KB units, the configurational entropy at the onset is a few units, and it goes to 0 maybe at this Scotsman transition. So in terms of absolute value, this is not a large number, and we'll need these numbers later during the lectures. So that's the very long summary. So we do this. This.
How is entropy calculated?
Thanks. I will explain this right now. So this is the goal of today's lecture. Okay?
What's happening along this blue line is more compaction or
Yeah, well, you undergo the glass transition as usual. So at the onset, you're a fluid. At the mode coupling transition, you have slowed down the dynamics by something like 5 orders of magnitude. At the blue box, the dynamics has slowed down by 12 orders of magnitude. And below, I don't know, because I would need to extrapolate. It's just a hard sphere system that's slowly compressed in equilibrium conditions. So it's the ordinary glass transition phenomenon as discussed by Gilles. So you'd have longer and longer relaxations, etc. Okay? So I skipped the thermostat, and then I assume that we have been able to do computer simulations at a given temperature. So we thermalize the system, and now we want to do measurements at this temperature. So I said, I think, and I hope I wrote this in my on the blackboard last time. I said the first part of the simulation is about thermalizing the system. So you thermalize at temperature T for long enough. Okay? And long enough means that you hope that the system has had enough time to reach the canonical Boltzmann distribution. So of course, the big question in the business of the glass transition is how long is long enough? Okay? And that's the big question, I think. And the question is, have you worked hard enough in order to establish that the system really had reached thermal equilibrium? So why is this the big question? It's because the whole problem of the glass transition is about beating the time scale of the slow dynamics. So of course, if you want your simulation to be at thermal equilibrium, you have to beat that time scale problem. So you have to fight hard. And of course, when the relaxation time is short, well, you have plenty of computer time, it's easy to thermalize. When you get to the end of your computer simulations, it's a bit nasty. And so the answer is we don't know. So there is no true hard criterion to prove you that any simulation has been able to thermalize. Okay, so what can you do then? You can try and do as many tests as you can. And this is how it's done. So you do all the tests that I'm going to list. And if they are all successful, then you may hope that maybe you have thermalized, but it's no proof. Okay? So there is no real proof for this. So the first thing that you would imagine that if you look at some simple quantities like energy, pressure, one-time quantities, so quantities that you can measure from a given snapshot, as I showed you last time, like the energy that you measure from the positions of the particle. So you hope that these one-time quantities are stationary. Okay, so maybe you will have an initial fast relaxation towards equilibrium, but in equilibrium conditions, things stop depending on time, so things do not depend on time. It's a nice test, because if it's not satisfied, you can see it immediately. It's far from being enough, because these one-time quantities don't tell you very much. Okay, so it's good, but it doesn't tell you very much, because glassy dynamics is about slow things changing very little the energy, for instance. So it doesn't tell you very much. So you can be a bit more demanding, and you can be interested in the fluctuations of these one-time quantities. So you could look at fluctuations. Okay, and we've seen examples in the first lecture. So for instance, if you look at the fluctuations of the number density, then we've seen that it follows a kind of a fluctuation dissipation theorem, and it's related to the isothermal compressibility like this. And the compressibility, I told you, is the derivative of the volume with respect to the pressure. So this is a derivative, so you could measure very precisely your equation of state, take the derivative, and compare to the spontaneous fluctuations of the density in your simulations. It's a very demanding test, it seems, because it requires that the system is at thermal equilibrium. This is a fluctuation dissipation theorem. So it looks very demanding. In reality, it's a very poor test. It doesn't tell you much about the fluctuation and the degree of thermalization of the system. And the reason that Giulio explained and Gilles explained many times, if you're in the liquid, all these things fluctuate and you have true thermal equilibrium. But if you're deeply quenched inside the glass, you have equilibrium within the glassy basin. And here again, this static FDT will be satisfied. So you see that FDT is satisfied in the liquid and in the glass. So as you cross the glass transition, if you're very precise, you see tiny deviations of this relation. It's super hard to see. It's even harder to see that as compared to doing, to ensuring thermalization. So there are many papers that base their thermalization on this. One that I like to cite is the paper in Nature by Werner Kraut in the year 2000. This is the only test for thermalization that he does in this paper. And he makes big claim from his state that he has thermalized the system at very large densities in hard spheres based on this relationship. So we don't know what this paper says. Okay, so that's fluctuations. So you can be even more demanding, and you can measure entire distributions. So I should use this one. Okay, so if you measure, say, the distribution of energies at a given temperature, you know that by construction, this is related to the density of state of the system times the Boltzmann factor. Okay, so this is the Boltzmann factor. And this guy here will come back several times during the lectures. Is the density of states. So the number of states at a given energy level. So if you invert this relation, you see that G of E is essentially the distribution times the inverse of the Boltzmann factor. And this guy is the density of state. It does not depend on the temperature. Okay? So it means that if you measure this guy at different temperatures in different simulations, the result should not change. So what you could do is you could, for each of your simulations, you could estimate from the measured distribution of energies during your simulations. You reweight this by the Boltzmann factor, and you should find something that does not depend on temperature. So if you follow equilibrium and then suddenly you fall out of equilibrium, you should see it, because at low temperatures, this guy will differ from the previous estimates at earlier simulations. Okay, so this is very bad too. Okay, it doesn't tell you much, and the reason is very simple to see, is that in any given simulation, the region of energies that you sample is different. So your estimates at different temperatures, typically they do not overlap. So when you put all of them together, it looks like a smooth function, but you really can't tell anything from this reconstructed density of state. Okay, again, famous papers that are entirely based on the idea that the density of state is independent of temperature. So one paper that I like to quote again is a recent one by the Berthier group, where they base their thermalization criterion on this rescaling of the density of state to make big claims again about thermalization that are not correct. Okay. So this is, as I say, a dangerous game. So the tests that I think are the most convincing are based on the dynamics. So you measure the dynamics of the particles, and you answer the simple question, do the particles move during your simulation? And if they move for large distances, then you can be reasonably certain that the simulation has sampled enough of the configuration space to reach thermal equilibrium. Okay? So you measure all the time correlation function that I showed you last time. You measure the, say, what I define as the self-relaxation time from the self-intermediate scattering function. Sorry, self. You can measure the collective one from the density correlation function, any time correlation function that you can invent. You can measure the diffusion constant of the particle by measuring the mean square displacement, and you make sure that the particles move a large amount, large distances during your computer simulation. And if it moves, then it's a very good suggestion that the system has reached thermalization. That's the best test, I think, to decide about thermal equilibrium or not. But it's really a big thing. There are many simulations or even experiments in colloidal systems, for instance, that do not satisfy this. Yes? So I'll show you that later. But typically what happens in a simulation is that this histograms like this as a function of energy. So if you do simulations at different temperatures, decreasing the temperatures, you find a typical distribution at the high temperature, another distribution at the lower temperature, etc., etc. When you reweight them like this, and you take, say, an estimate for this, you'll have sorry. Let me erase this. Your estimate of the density of state in a log scale, say. So these three simulations, they will look like this. Okay? And then you will adjust the vertical axis so that they look like the continuation of one another. And typically you will reconstruct a curve. But what you don't do is you don't compare the entire density of state at one temperature to the estimate at another temperature. So you don't see whether you really reconstruct the same density of state. With the part that looks the same, but you really don't know whether you have the entire distribution of states correctly. And we've worked hard, and we've produced configurations that were out of equilibrium. We knew that. And you can reconstruct beautifully the density of state, apparently. So we know that when you're not thermalized, it seems to work. Okay, so you do all your stuff, you believe you're thermalized, but then comes the problem of the glass transition again, which is okay, we avoid talking about the crystal all the time, but it is present all the time, and it makes things very complicated. So again, Gilles said it's super easy to not crystallize. I said it's not. So how do you decide whether the system has crystallized or not? Again, it's very difficult in general. Okay, so for instance, you would follow. So the ideal case is you would follow the pressure in your system during your thermalization. It would look super nice and steady, and then boom, at some point, you have a first order jump towards the crystal. Okay, so this is the ideal scenario where you think you're doing a good simulation, and you can realize that it's a bad simulation. Okay, so this is the ideal scenario. It almost never happens like this in reality. In reality, you see a time series of the pressure. You have these slow fluctuations. Maybe it goes down and up, and you really can't see anything. And at the end, you watch your configuration, it's a crystal. You haven't seen it happen. Okay, so life is much harder. Okay, so it means that you have to watch at the structure. So you have to watch at the pair correlation function. You have to watch the structure factors and as many static quantities as you can, and you have to essentially watch the configuration in real space to decide whether you have a crystal. There are many other parameters that are defined that I won't have time to discuss today, but there are many static quantities that have been devised to really detect crystalline order in your simulations of supercooled liquid. And again, you have to check them very carefully all the time if you want to be sure that the system has not crystallized. Again, there are many papers that are based on crystallized simulation. I won't cite any name today. Sure? Yes? Well, no, so as you said, I mean, they contain in principle the same information, but in different representations. So sometimes the crystal is more easily seen here, sometimes it's more easily seen here. It really depends on what type of crystal. And typically when I say the system has crystallized, it's typically that you have your simulation box, and there is a little piece of crystalline material somewhere. So if you measure some global quantity here, it will be not too clear that you have a crystal somewhere. Maybe sometimes this guy will have a sharp peak because of the... So there is no rule. So you have to watch them all. That's what I'm saying. Everything can happen. And, you know, I say that we, for instance, work with these mixtures. So sometimes what's happening is that you have a partial demixing between small and big particles. And then, for instance, the big one will start to make a crystal. So it's really typically a complex process. It's not, you know... So what you're saying is about this ideal case where you have nucleation and then you have an entire crystal. It never happens like this because we have worked hard to fight crystallization. So crystallization is very frustrated, but it takes place nevertheless. Okay. So in principle, we have thermalized. We have introduced the temperature. We have verified that the system has not crystallized. So we have a series of configurations, out of which we know how to compute many, many different quantities. So we are ready. Okay. So we are ready to start and do measurements related to the physics of the glass transition. Well, I said some are worse than others, and I said the most stringent thing is about looking at the dynamics. And of course, it relies on the idea that you have the real dynamics taking place in the system. So one of the papers that I think I didn't mention was using the density of state rescaling to judge thermalization. It's because they were using parallel tempering, where you have your series of simulation and you exchange configuration between neighboring temperatures. That means that at any given temperature, you cannot follow the dynamics of the particles. So there are simulation techniques that are supposedly helping you to thermalize, but they remove the dynamic part of the simulation and they focus on the statics. So what do you do then if you don't have the dynamics? You're left with this series of very bad thermalization tests. So it's a dangerous game, okay? And the parallel tempering papers use the density of state, so you can't say whether they were thermalized or not. You have no idea.
And is it sufficient to look at mean square displacement curves?
Well, no, as I said, nothing's sufficient, okay? Yeah, but if you have a simulation technique that helps you access temperature that you cannot simulate with ordinary simulations, if you do this, then they will be stuck. And how do you decide whether? So once you don't have the dynamics, it's pretty hard to convince anyone of thermalization. And so you do your best. So all of the tests must be, of course, successful. If you fail, then So we're ready. So we want to answer his questions about how do you measure the blue curve, and this is what we are going to do now. So the blue curve, I think, was the configurational entropy. and it was estimated like this: S start minus S bib. So it has two pieces, and we'll estimate the two pieces separately. So the first piece is about evaluating the entropy. So that's what I'm going to do now. Okay. So the system I showed you was a hard sphere system. So for hard spheres, the estimate of the entropy is not too complicated because you don't have energy. Remember that the pair potential for hard spheres is either 0 or infinity. And so in an equilibrium simulation, it's 0. Otherwise, you would have an infinite overlap. That's forbidden. So it means that essentially the entropy for hard spheres is just the free energy. So we have to estimate the free energy for a hard sphere system. So the way we do this is by starting from the state point where we know exactly the free energy, say the ideal gas, and then we go to the point where we want to measure the entropy. So that's how we do. So we do that. So I'm changing notations constantly in my notes. So this is the total entropy. Okay, and I just said that the total entropy is the ideal entropy of an ideal gas of hard spheres. So that would be valid at very low densities, plus an excess entropy. Okay, so that's the ideal gas entropy. And that's the excess part that comes from interactions between the particles at finite density. So the entropy of the ideal gas, I think you know it from the textbook. So I just take this formula from textbooks. Okay, so it's 5/2 minus log of the density, and I think the density, I was defining it as rho 0 last time, minus the log of the de Broglie wavelength cube plus a mixing entropy term that I'm going to discuss later. Okay, so that's called the mixing entropy. So if you have identical particles, this guy disappears and you don't even have to think about it, and this is the ideal gas entropy. Okay, and the mixing I will describe in a second. And the excess part, I said you do it by thermodynamic integration, and this is the expression. It doesn't really matter, just to give you an idea of how we do it in practice. Okay, so you start from a very dilute system, you go to the density at which you want to estimate the entropy, and you do a thermodynamic integration of the pressure divided by rho squared, I think. That's it. Okay, so this is a thermodynamic integration. So in a computer simulation, what you would do is you would prepare a series of configurations at different densities between 0 and the density at which you want to estimate the entropy. You would measure the excess pressure at each of the density, and then you would perform this integral numerically. You get this number, add to this number, and then you would get an estimate for the total entropy of the hard sphere system. So it requires that for each pressure, each density between 0 and the density at which you want to work, you have a large number of equilibrium configurations. Yes?
What is the excess? This is a non-ideal part.
Yeah, again, so the excess pressure is the pressure minus the pressure of the hard sphere gas. So you okay. So the physics is the pressure that comes from interactions between the particles, you know. Yeah. Okay. So I have it here. So it's 2 pi beta a squared. That comes from integrating the momenta. Okay. Okay. So this is low. So what about this mixing entropy? It's not terribly exciting, but we are working on it at the moment, so this is exciting to me at least. So I told you to avoid crystallization, we take binary mixtures or continuous polydispersity, so distribution of particle sizes. So if you have two species in the system, it means that even for the ideal gas, you have an entropy that comes from interchanging the identity of the particles. Okay, and you've done a lot of exercises about this paradox that comes from exchanging the identity of the particles. So if you have a mixture with m components, okay, so what is this mixing entropy and where does it come from? So the concentration of species m, I will call it xm, and so it's the number of particles of identity m divided by the total number of particles. So that's the notation. So where does it come from? So when you compute the partition function for such a system, you'll have a prefactor term that will be like this. Capital M. You have the factorial n of everybody, then the de Broglie, and then this integral over the Boltzmann weight. So the mixing entropy comes from this factorial prefactor. So when you'll want to compute the free energy, so when you'll want to compute something like minus beta f, you will take the log of the partition function. So you will have a term which is the log of this product of factorials like this. So you'll have a term that looks like minus log of this product. No, never this one. Okay, so if you take the log of this guy, and you use the Stirling's approximations, so you'll have a term that looks like this. So you can do it, but I'll go a bit faster. You'll have a term where you'll have only the total numbers of particles, and then minus a term which will be like this. Okay, so this is the term you would have in the monocomponent system, so for identical particles. So this is the usual term that you have for identical particles. So this additional term to the free energy, this is precisely the mixing entropy. This is the term that comes from mixing the different densities. Okay.
Without the prefactor n?
Sorry?
Is that S mixing without the prefactor n?
So it's n times this. Okay. Or if you wish, this is the total with the capital S. Okay, so let's see what this term contains. So imagine that you have a binary mixture. So you have, say, two sizes of particles, big ones and small ones, and their concentration is 1/2. Okay? So if you plug 1/2 in this term, so you have twice the same thing. And if you put everything together, you realize that the mixing entropy, this is log 2. So log 2, it's about something like 6, 9, 3. Okay, so it means that in the ideal gas entropy, you have a term that you add, which is of order 0.693. So if you remember the number that I gave you in the figure for the configurational entropy, the number were of order 1, and the total entropy was changing from 2 to 1 to 0.5, something like this. And the determination of the Boltzmann transition is about to find when this entropy is going to 0. So of course, if you make a mistake of order 0.7 because you forget the mixing entropy, it's very complicated. It will change the estimate of the Boltzmann transition by a very large amount. So taking care of the mixing entropy, even though it seems to be a feature of the ideal gas, it's very crucial in, say, when you want to predict the location of the Boltzmann transition. It's a very big contribution. And we tend to think now that this estimate that we do usually in computer that people have done in computer simulation is probably wrong. And this guy probably should be taken into account more seriously. It would become a temperature-dependent function that nobody has measured yet. So it means that presumably we've done approximations that were very bad previously. So that's for getting your interest.
So does this depend on temperature because if dense configurations you can't just exchange two particles and still be in equilibrium?
It's a very long story, so I won't answer it now, but I'm happy to discuss it with you later. So this estimate of the ideal gas entropy has no problem. So the difficulty is when you want to subtract a vibrational contribution, you have to decide what to do with the particle exchanges, and this is where things get complicated. So it's because the system is dense, indeed, you're right. Yes?
Somewhat, well, question stimulated by this discussion. So let's say you're simulating, slightly polydispersed. I didn't read the rest.
You're cheating, Leo. So let's say we simulate a distribution with a slightly polydispersed, If you have a continuous distribution of particle sizes or distribution of particle diameter like this, because you have synthesized a particle, then you have a distribution of those because each colloid is different from another colloid because it's made of a large number of atoms. Okay, so it means that each particle is different. So it means that the concentration of a species m is 1 over n. Okay. So a system is made of n species because all particles are different. So we would say that particles are now distinguishable. Okay? So if you impose that xm is 1 over n and you do this sum here, so it's 1 over n sum of log of 1 over n multiplied by n, it means that the mixing entropy, okay, it has a term which is log n, so it's diverging. So if you were to apply blindly the formula that we were given to compute the configurational entropy for continuous polydispersed system, then you find that the entropy in the liquid is infinity because you have so many states because each state is counted differently. So that's a problem because then, if you want to find a phase transition based on the fact that the entropy goes to 0, but the entropy as defined in the liquid is infinity, it's never going to take place. So that seems to suggest that in a system with continuous polydispersity, you would never have a Kaufman transition. And as Leo was about to ask, that sounds stupid. Because imagine that you have a distribution of particle sizes that is extremely narrow, of width much smaller than the typical size of the particles. Then physically it would seem that these particles are all the same from the point of view of the physics. Okay, so if you have a distribution that's like this, okay, and this is the average of sigma, and this width here is epsilon much smaller than sigma 0, you would expect that the system behaves as a monocomponent system and the entropy of mixing should be irrelevant. Okay, so something's wrong and fishy in these estimates of the mixing entropy. It means we need to do better and estimate better the mixing entropy term. And this is what some people here are trying to do.
Well, isn't it because there is Sermon approximation?
No. You have a large number of particles, so you can use it. So that's not the approximation. As I answered to him, again, and we are going to estimate in a minute what this vibrational entropy is about. So the total entropy is the total entropy. There is no issue with that. So the mistake that is made is, what do we do with the vibrational entropy? And so that's the next chapter. So please ask the question again when we've done the vibrational entropy. Why was there a problem with the mixing entropy after the calculation? Okay.
It's simple because I can't quite read it.
Oh, sorry.
But why is there not an n in front of log n? It's 10 log n.
So it's 1 over n sum, 1 over n log 1 over n, but you have an n here.
Right, there should be n in front, right?
Yes. So maybe this is. Yeah, thanks.
But is that right? In itself, it's not. You have already n-log n.
Yeah, but if you think of the monocomponent system, you also have the n log n factor in the vibrational entropy, and they cancel. Okay, so now it's about estimating this vibrational entropy. Okay, so we go to the most naive estimate of this, and I have also numbers for my sections, and this is the third section, so it's called the potential energy landscape. Okay, so what is the vibrational contribution to the entropy again? So you remember this picture that everybody draws and apologizes after, oh, it doesn't mean anything, but I do it nevertheless. And everybody's doing it, so I do it just to follow everybody else. So we have this landscape idea that you have states separated by something. We don't know what the states are, and Giulio demonstrated that states don't exist anyway. Okay, so so we don't put axes because we don't know what the axes really mean. And we say when the system is somewhere in one of these states, it's doing vibrations. Okay, so we want to remove the contribution coming from sampling many configurations inside the same basin here, and we want to remove this trivial contribution to the entropy. So this is done in experiments, and this is how I'm going to do right now. Okay. So we have to decide what we call states and what we call vibrations now. So we said in mean field these guys should be metastable states, and in mean field everything is well defined, so we can really put the system there and do a thermodynamic integration within one of these well-defined free energy minima. Okay, this is what Giulio did, I think, twice. One in the lecture about the random energy model, and one in the lecture about the mean field theory of the glass transition. So he did that calculation twice of the entropy. So because in finite D we don't know how to define the free energy states, one idea that has been suggested is to replace the free energy states by energy minima. Okay? And in the lecture by Gilles, he said, but if we go to 0 temperature, you freeze the system at 0 temperature, you look at the energy landscape, everything is well defined. So that's the viewpoint that I'm going to take in section 3. You go to energy minima of the system, and the energy landscape now, it's a well-defined quantity. I can talk about energy minima and basins of attraction of energy minima. So everything becomes well-defined, so that's good. There is no idea that you will nucleate one state into another, destroying the states, internal inconsistency. This is all very much consistent. But of course, you already heard Gilles' lecture, so you know that. He said something very strong about the energy landscape. He said we don't learn anything from studying the energy landscape because maybe it has nothing to do with the physics at finite. You say it's this. You said it's unrelated to the physics. That seems strong to me. So at least it's a well-defined partition of the configuration space. So why not try and use it and see what you get out of it. Okay, so this, I think, idea of defining the structure at the level of the potential energy landscape, it probably goes back to Stillinger and Weber, and maybe earlier, but at least they have formalized it, and it goes, I will put references sometimes later this week about all the lectures and the important papers that I've quoted. I will put them on the website of the school, so you don't have to think too much about it. So the idea of Frank Stillinger is, as Giulio did already, is to decompose the partition function, which is normally a sum over all the configurations like this. So let me try to use the same notations always. Okay, so this is the partition function where you would sum over all configurations. And in the decomposition in terms of the energy landscape, you would say this is a sum over basins, and basins are labeled by alpha, of the partition function restricted within one of these basins. Okay? And now basins are defined by being close to an energy minimum in the potential energy landscape. Okay, so that's a partition of the configuration space. So you do this partition, and then you try to estimate the partition function within each of these minima. And then you reconstruct the statistical mechanics of the system.
Count all the second points.
Sorry?
In the second inequality, are you trying to count all the second points?
No, I'm telling you that I'm partitioning the. Okay, so it's like this. Okay, so this is one basin close to an energy minimum alpha.
Are you doing this with energy or actual energy?
Energies.
So for hard spheres, there is no energy.
Yes, you're right.
Talking about
Yeah, so at the end, I will tell you what I do for hard spheres, because the figure was about hard spheres. So I don't do this, I do this for generic liquids, and then I will say for hard spheres it doesn't work, and I will tell you what can be done. Okay? Okay, so let's do the partitioning. So we now say that these labels alpha are for energy minima. So I will say that Z alpha is really the partition function within close to one of those. And close means that I really assume that the energy, I will explain the notation in 1 minute. Okay, so in this diagram, in the basin alpha, I would say that there is a special point here. So now this is really the energy. So this is the potential energy landscape that I can probe. And the energy of this guy here within the basin alpha, I call it EIS of alpha. And IS stands for inherent structure. That is an energy minimum in the landscape. So this is an inherent structure. This is the name given by Stillinger and Weber to energy minima. And so I put the symbol alpha to say that this is the energy of the inherent structure alpha. Okay, and I said the energy is very close to this one, and I have essentially further approximation. I will assume that I have something like harmonic vibrations around this energy minima. So you do the harmonic approximation. Okay, and you write down that this energy is the energy of the minima. So because this is a minima, the first order term of the expansion disappears, and you're left with the second order thing, which is sum over ij of I or j. Okay, so this is just a second order expansion of the energy. And the matrix that appears here, it's called the Hessian. So it's the matrix of the second derivatives. It's giving you the curvature of the energy potential, the potential energy near the energy minimum. Okay, so this matrix you can diagonalize, introduce the eigenvalues, eigenvectors, and finish this. Okay, so this is alpha, plus I will introduce the eigenvalues, which I will call omega. So I have a 1/2. So I have 3 ends of these eigenvalues, which I call omega A of alpha squared. Okay, so these are the eigenvalues of the Hessian, which I have diagonalized. And this is nice because this is just then a harmonic expansion, so I will be able to do this integral exactly. This is a Gaussian integral. Okay, so I will give you the result of this Gaussian integral, and then I will take Patrick's question. I don't. Aha. Thanks, Patrick. I mean, I wanted to skip that discussion, but what I do here, I say that within one basin, then I can, do a permutation of all the particles. I have factorial n of those contributions, because the inherent structure is invariant under permutations. So the factorial n disappears. Of course, when you have mixtures, okay, you have to decide to do something there. So it's exactly the point where the mixture appears. What you do with the factorials when you have different types of particles.
Sorry, I was saying in a fixed basis, particle becomes distinguishable because the configuration is specified.
Well, if okay, thanks, Patrick. So let's suppose that we have identical particles, okay? And then I will answer your question again for mixtures of particles at the end of the calculation. So for identical particle, if I go to an energy minimum, I have each particle in a given position. But if I exchange two particles, it doesn't change the configurations because they're all identical.
But that should be another alpha. That should be labeled by another alpha, right?
Sorry?
If you exchange two particles in a different configuration, that's labeled by different alpha.
But how can you tell that the two configurations are different? It's the exact same configuration. So I have to count all of those as contributing to the partition function. So of course, when they are not identical, you have to decide whether this is allowed or not. And this is the key point of the story I was telling you before. So I do this calculation. If I want to go a bit faster to this, then so you rewrite this integral over the Boltzmann way. You put out the exponential minus beta energy. Then you do the Gaussian integral, and you end up with something like this. So this is alpha minus a vibrational configuration, okay? A vibrational contribution, which I can rewrite like this. And this is really the result of the Gaussian integral over the 3n eigenvalues here. So I just give you the result like this. It's minus 1/2 sum over a log of beta h bar omega a square divided by n. So again, the final expression doesn't really matter. I just tell you that we have a vibrational contribution to it. Okay, so we have z over alpha, so we can finish the partition and compute the partition function for all the system now.
Compare the harmonic approximation. We know we're integrating over the whole basin, and it breaks down the edges are like most important.
So people have gone to third order. Sometimes it's big, sometimes it's small. So for the hard sphere system, we did it also. It's super small. For most of the systems I have looked at, it's super small. So I don't understand what systems it's good, for what system it's bad. But anyway, you have to remember that the line 1 here, it's totally, conceptually it's totally weird. No? So we are doing something weird in terms of decomposing phase space. So of course, once you've made the decision, this is how I'm going to compute the configuration and entropy. You want to do things as good as possible, but the corrections you do here is big or small, but the entire approach is a bit sketchy. Okay. Okay, so I have this guy. So I go back to the total partition function now. So this is z. So that was this sum of alpha of z of alpha. And now I do essentially what Giulio did twice. Okay, so I rewrite things like this to introduce the density of state. So I have this integral of a delta function. Okay, so I just introduce 1 by this delta function, and I invert to introduce the density of state. Okay, so this is integral d. Okay, so this is dependent of EIS of alpha. Sum over alpha delta EES minus EIS alpha. And now because I have the delta function, this guy depends only on IS. Okay, and this is the density of state. So this is really the number of states that energy minima that have energy EIS. So I define this guy as this number, and this is exponential times, well, let me call it SC, the configurational entropy at the value IS. Okay, so Giulio did it twice, so I do the same. And then we are left with this integral over IS, where I collect all the pieces, and it looks like this. So Z is integral DIS exponential minus beta EIS. I had the vibrational contribution, which I call FVIB, and now I have this entropic term that comes from the density of states. Okay, so I could make it even more even closer to what Giulio did. I define this guy like this, and I'm left with something that looks like exactly the same quantity. Okay, so I have exponential of SC minus beta F basin, and all these two things depend on EIS. Okay, so all these quantities are extensive, so I have an n in front, so I have to solve this by saddle point. So this is again the same. Okay, so you do the saddle point approximation, and you get an expression for Z. So this is what Giulio did in lecture 1 and 3 twice. Okay, so the saddle point is given by d SC divided by d is equal to beta df basin by dis, and that defines the saddle point. So if I put that back into the integral, I have an expression finally for the total free energy, and this is why I want to stop that calculation. Okay, so finally we get that by this partition we get that the free energy is minus beta times F basin taken at the saddle point minus T SC taken at the saddle point. So we have an estimate of the free energy, so we can extract the entropy, and we can extract the configurational entropy. And in this partition, we realize that S is really the total entropy minus the vibrational component. And so we have an estimate now for the vibrational component of the entropy. This is the sum of eigenvectors, eigenvalues of the Hessian there. So this is all explicit, if you wish. Okay. Explicit expression. Okay, so we used the same definition as before, but now we have specific, we have equations to estimate these quantities. So we have already done the job for S stat, so we have to do the job for SVIB now. So what does it require? So in practice, okay, so S stat, we've done it before. I told you the thermodynamic integration. So what do we do for SVIB? So for SV, we have to go to energy minima. At the minima, we have to estimate the Hessian. We have to diagonalize the Hessian and get the eigenvalues. Okay, so we need to do this. Okay, so the first thing we need to do, we need an algorithm to find energy minima. Okay, that is, it's an algorithm that takes an equilibrium configuration at temperature T. It has to find the closest energy minimum to it. Okay, so you have to have an algorithm here. And then you have to find the inherent structure of that guy. So who has already done energy minimization to find inherent structure? Eric? Okay. So what's the name of the algorithm you use? Patrick? See? What is fire?
It's the algorithm with inertia.
Okay. And what's the idea of the algorithm behind?
It's basically steepest descent plus inertia, but quicker.
Okay. So conjugate gradient, how does it work? What? Magic. Yeah, exactly. Well, I've never done it myself, so I asked everybody last week, what do you do? So they answered like this, and at the end of the day, but how does it work? And then they sent me these PDF files on how the conjugate gradient method works. It's not that difficult, but it's not totally trivial either, and it's not super interesting in the context of these lectures. So I could give you references, but it's just a straight and simple algorithm. You essentially copy, paste something from the web usually, and someone has done it for you, or there are existing softwares like Fire that do it automatically. There was a question somewhere? Yes?
You assume F is independent of alpha?
Yeah, or what? Yeah. So what you could do is you could measure this for large numbers of different energy minima and take the average at the end.
And what about the negative eigenvalues?
But this is an energy minimum. So by definition, you have only positive curvatures in the minimum. So that's why you can diagonalize it in the first place, by the way. Frankly,
Not always, actually. And then there's another line search algorithm for DSGS that are also used. And they use
yeah, so that's a whole industry of people trying to find, and there are different methods. They are more and more elaborate to find the closest to you or the next. They have their good and their bad, and again, if you want to do it, you have to read a little bit what they do. But But for normal liquids that are not too close to jamming, or that don't have stupid interactions, the simplest one will work, and presumably they will all give them the same results because the partition is well enough defined. Okay, so we have the inherent structure because we have a magic algorithm. Okay, so we can then estimate the Hessian. We take the matrix of second derivatives. And then we have to get the eigenvalues. So again, it's a problem in diagonalizing large matrices. So who has done this before? Patrick, you did everything. Lisa, you did? So what do you use? See, software. You go to the internet. And again, this is magic. Okay, you don't even have to know how it works. Okay, unless you run into problems, and then you have to decide whether your algorithm is good or bad. And then you have to go back and learn those things. Okay. So out of this, you get all the list of eigenvalues of the system. Okay, you have 3n numbers. So typically what you do, you would group them into a function which would be the density of states of eigenvalues. Okay. Magic means it's a black box. Okay, so you get a function which is the density of state of eigenvalues. So of course, it gives then access to the vibrational contribution to the entropy, but there are large numbers of problems where you would be interested of the density of states of this Hessian close to this inherent structure. So, for instance, people interested in low temperature physics in glasses. Okay, you take a glass, you go to very low temperatures in the glass phase, and you look at the physics, transport properties, etc. You would be interested very much into the properties of this G of omega. And Giulio mentioned, and I mentioned it also, that several people in this room are working on this Gardner transition, which is reflecting in the low temperature properties of these glasses, and it manifests itself normally in the density of state. You will have talks about the jamming transition. Okay, so it might be that Lisa Manning is going to talk about it, and Carlo is going to talk about it, and they will talk about the idea of soft modes, modes that have extremely low frequencies in the density of states, and you will hear a lot about that physics later. And the Gardner transition is a way to connect these two ideas, by the way. Okay, so that's density of state. So now we have everything. We can compute the vibrational contribution to the entropy. We can subtract from the total entropy. And then we have computed the blue curve in the figure. Okay. Sorry, Eric?
Are you saying that you only need to find one energy minima?
No, you do many, and then you do statistics of those, and you average over everybody.
So you have to assume that the ones that you
Well, if you had an infinitely large system, that would be enough, probably.
but you don't have to enumerate.
No. You take just as many as you can, and that's enough. You just check that the result is converging quickly enough. Okay. So I think we are done with the calculation of the configurational entropy from this partition of the landscape. I have to go faster, I think. So skip this. So you want to know how we do for hard spheres, Eric, or we can skip that? Okay, so we have a method for hard spheres. Ask me later, and I'm sure I can continue with this. Thanks, Eric. Maybe the one sentence I will tell you that the method for hard sphere, it would work for ordinary liquids with continuous pair potentials. It means that for those liquids, you have two methods that give you, in principle, the same estimate, or the philosophy behind is the same. They tend to give different quantitative results. So even though you do your best within one approximation, the final results are different. So it's telling you that the idea you started from, it's a bit difficult to define. Okay, so I want to now compute the other curves first, and I want to also access a temperature regime that's close to the experimental glass transition. So that's the goal of the section 4 of the lecture, which is about getting faster towards equilibrium. And the way I will go faster towards equilibrium is by shifting from molecular dynamics simulations to Monte Carlo simulations. If you want to go faster with Newton's equation, I don't know what you can do because you have no degrees of freedom there. You just have to run the equations of motion, and the particles have to move. You have to discretize your equations, and that's it. So you have nowhere, in the algorithm, there is no place for speeding up the simulations. So you're stuck with molecular dynamics. So you have to turn to a different type of simulations. So I say I will called Monte Carlo simulation MC. So that will be a short crash course on Monte Carlo simulations. It's 1 page. Okay. So you can define this as a stochastic Markov process to very efficiently sample the configuration space. And that's it, okay? Okay, so stochastic means that it's not deterministic as Newton's equation. So stochastic means that it's non-deterministic. And then it's different from the Newton's equations that are behind molecular dynamics. And because it's not deterministic, you have a choice in the probabilities for the random processes that you will use during the process, and this is what is allowing you to get faster. Okay? So that's the interest of the Monte Carlo simulation. So Markov. Okay, so let's assume that you have, so very quickly, if you have a random process as a function of time like this, okay, so x of t is a random process, and you want to define what it means to be Markovian, for instance. So if you observe the value at time t1, t2, TL of this process, if you want to specify entirely the properties of this process, if it's a general stochastic process, you will need a quantity which is WL for x1, t1 up to xl. Okay, you would require this entire probability if you want to describe the statistics of this process. So Markovian simplifies a little bit, the statistics of these objects, and it's telling you that if you want to estimate the probability with L plus 1 events, x1, t1, xl plus 1 at time tl plus 1, it will take the form of something like this: x1, t1, xl, tl times a conditional probability, which is xl, tl times, sorry, it's too small, times p, xl, tl, xl plus 1, tl plus 1. So this is, okay, so it's just telling you that the process has essentially no memory of the past. Okay, you go up to L, and then the step from L plus 1, it only involves the conditional probability. You don't need to know what happened before. So it's something which is memoryless, if you wish. Okay. So it means that the key quantities that you have to study for Markov process is this conditional probability to go from one event to the next. Okay. Okay, so this is a probability. If you take the limit of time going to time differences going to very small, you'll define transition rates, and this is what's needed to obtain an equation of motion for these Markov processes. I go directly to the result to go faster. And what you have is that probabilities follow the master equation. So this master equation, in a sense, is the analog for Monte Carlo of Newton's equation. These are the. So this is the equation of motion in Monte Carlo process, if you want. Okay, so I define P of x and t, which is the probability that the process has the value x at time t. So that's the probability. and I want to get an equation of motion for this probability. Okay, so this guy, that x. Okay, so if I define something like this, this is all very formal, we don't really care. So you give yourself some initial condition, x0 times 0, and then you introduce this conditional probability I introduced over there. Okay, so that by definition we get the probability that you have x times t, and the other quantity I want to introduce is the transition rate. And I will define it like this, which is the limit when the time goes to 0 of this conditional probability divided by t. If x0 and x are different. So that's all I need to define the equation of motion. Okay, and then the time evolution of this probability is given by something which at the end of the day looks very simple. So it's p of x prime t times. Okay, so this is the gain term, and this is minus p of x. Okay, so this is the equation of motion if you want for this probability. So if you have a discrete configuration space, like if you have spins, the integral over dx become a sum of configurations. Okay, and so you'll have essentially the same equation of motion with a discrete sum here with probabilities and transition rates. Okay. Yes, like this, so it's different from Guillaume, I think. Who so this is the initial condition, so that's giving you the time order. Okay, so quickly the idea of the Monte Carlo. If you want to reach the equilibrium distribution, okay, so you want this guy to be stationary at equilibrium, so you want that the equilibrium distribution satisfies this. So it means that in this sum on the right, you have this sum should be going to 0. Okay, so you've probably all done this many times. We'll put it in the middle. Okay, so if we want this to define these transition rates, we use the condition which is called detailed balance. And so we say that each term is the sum is equal to 0. Okay, so we say that inside this bracket all the terms are 0 separately, such that the sum is equal to 0. Okay, so in the case of the discrete sum, it means that the transition from C prime to C divided by the transition from C to C prime is the distribution of C times the stationary distribution of C prime. Okay, something like this. And if you want to sample the canonical distribution, then this guy will just become the exponential of minus beta h of minus C prime minus h of C. Okay, so that's the condition for detailed balance. So provided your transition rates satisfy this, then you'll sample the equilibrium canonical distribution. So I wanted to do this. Okay, so it's possible to prove that if your transition rate satisfies detailed balance, you start from some initial conditions, then by this master equation, the probability distribution will reach the equilibrium one at large times. This can be proved. So that justifies the Monte Carlo algorithm. You define a stochastic process that satisfies detailed balance, and by construction, the algorithm will be sampling the configuration space with the canonical distribution. Okay, so that's the idea behind the Monte Carlo, which is nothing magic this time. Okay. So Monte Carlo, you have transition rates obeying detailed balance. Okay, so it means that you sample the configuration space. With the probability that you have chosen the equilibrium probability. Okay, so that's it. So the simulation I wanted to show you in the first slide was simulations of hard sphere systems. So how do you set up a Monte Carlo simulations for hard sphere? So you have to take your configuration of hard spheres. You have to, say, propose a different configuration and accept or reject this configuration with a transition rate that obeys detailed balance, that satisfies this thing. So of course, because in hard spheres, the Hamiltonian is either 0 or infinity, it's super simple to set up a Monte Carlo simulation. So you have your configuration C. So this is what we do, super complicated. You pick up one particle at random. Okay? You try to make a move, and you choose some random displacement for that particle. And if that move does not create an infinite energy, then you can accept it. And that's it.
Is there anything special about moving them particle by particle rather than moving the whole system?
Okay. And then you accept or reject, depending on whether or not you create an overlap with another hard sphere. So you take a particle, you move it. If it does not create an overlap, you're done. You have reached another configuration, and that's it. And because these guys satisfy detailed balance, you will be sampling the Boltzmann distribution for this hard sphere system, and that's how you thermalize the system in Monte Carlo simulations. You don't solve any complicated equations of motion. It's very fast, very efficient, but of course it has nothing to do with the real thing. It's not what you would observe in the confocal microscope for real colloids, for instance. Okay. So you have a way to sample configuration space, but the dynamics has been screwed completely.
How do you ever get an accepted move if you're in a really dense spot?
So that's really dense. So if your moves are not too big, then that's it. Okay. So you just optimize if you wish the typical size of the jumps. Of course, if you take this guy and you want to jump it here, there will be someone sitting here, presumably. So the moves have to be comparable to the size, to the typical vibrational length that you have.
Practice, how do you determine where this back object is according or not?
Well, you hope it is, and well, what you do, you're never sure. I mean, how do you prove that your system is ergodic? You just check that nobody's, blocked somewhere that you can. Again, what we typically do, we check that all particles are traveling across the boxes many times, and then you say, okay, presumably the thing is ergodic. You're never sure. Okay. Good question. Okay, so dynamics is lost. It's totally unphysical. It has nothing to do with the realistic equation of motion. So it's an efficient way of describing, of sampling the configuration state at equilibrium that the dynamics totally lasts in principle.
If the dynamics is different from the physical dynamics, why the approach in the non-equilibrium regime is different, is also different?
Yeah, so in principle, I'm going to say that if you want to study the dynamics, you have to work harder and you have to prove that it gives you something which is meaningful. That's what I want to do now. You know, in principle, you should remember that Monte Carlo is not about the real dynamics. Okay? So there is one limit which is, well, at the same time nice because it connects to the physics, but it's not nice from the point of view of the simulation, is that if the jump length is really becoming very, very small, it means that each particle is doing these small jumps. So this, by construction, then you connect to something which is called the Brownian dynamics. And the Monte Carlo simulations becomes equivalent to Brownian dynamics, which is the physical dynamics. So this is the overdamped limit of the Langevin equation. And it's probably relevant for the physics as observed in the confocal microscope, for instance, for colloidal systems. So there is a limit at least where you connect to the physics and where you believe the dynamics is physical. Okay, so that's the physics of a big tracer particle immersed in a solvent, if you wish. Okay. For finite delta R, there is no proof. But if you do a computer simulation of a glass-forming liquid approaching the glass transition, you measure the time correlation function I told you about before. You extract the correlation times, the relaxation times. You compare that to the Newtonian dynamics, and it's equivalent. Okay, so that's a strong result. It's strong because it's not proved or expected naturally. But the Monte Carlo dynamics, it's really equivalent to the MD dynamics. It's equivalent in the sense that the temperature dependence of all the quantities seems to be following each other. And that's a very strong result, I would say. And the physics behind is probably the strong separation of time scale. Which is, again, this picture of the system spending a lot of time in some minima that we don't know how to define and making jumps very rarely. And so if you have this strong separation of scale, it might mean that what you do at the microscopic time scale is totally irrelevant. And really what matters are the large-scale properties of your landscape. But again, it's not guaranteed. You have to work hard, measure all these things, and then you obtain as a result that the two dynamics give you similar results. And then that helps because it means that you can use the Monte Carlo simulations, even if you want to study dynamical processes, which is answering his question. So in principle, it's wrong for the dynamics, but in practice, it turns out to be very, very good. So I want to take 5 minutes to finish this. Okay, so how do you go faster then? Because it seems that I just told you that if you do Monte Carlo or molecular dynamics, you find the same temperature dependence for the relaxation times. So it's good, but it's then as slow as the molecular dynamics. You haven't gained anything. So the trick, if you want to try to go faster, is to invent more complicated mode. And that's Eric's questions. Okay, so I told you for hard spheres, you pick one particle, you try to displace it by a small amount, and you accept or reject depending on whether you create overlaps or not. But what is preventing you from, using 2 particles, more particles, and etc.? That was your question, I think, Eric. So let me give you 2 examples of this. So there is one example that goes back to Werner Kraut and Etienne Bernard. It's a Physical Review E paper from 2009, and they essentially followed your remark, Eric, and they said we'll displace many particles at the same time. So it's called event chain. So So I won't describe it in a lot of detail, but you always have this picture of a dense liquid. And instead of taking one particle and displacing it, they start with one particle, they displace it until it hits one particle, in which case they take this one and they displace it until it hits one particle, etc. And then they have a way to cut the chain length at an arbitrary number. So they really move a chain of particles in a given directions like this. Okay, so they move chain of particles. So then you have to check that you satisfy detail balance and everything. You have to check reversibility, ergodicity of the algorithm. And they did a lot of work on the melting of identical spheres with this algorithm. It's not clear to me what they do for what the algorithm does for a glass. And I have to say I would like very much to know the answer quantitatively. In this paper, they say that the acceleration it's a factor of 40, so it's 40 times faster than the ordinary Monte Carlo simulations. And they compare that to molecular dynamics, and the acceleration is a factor of 4. But they haven't tried it in a glassy system. I would be happy to try it at some point, but I didn't have the time to try. And this factor 40 is not really encouraging because they were not yet in the glassy regime. So my suspicion is that it doesn't help very much for dense liquids, but I don't know. I might be very wrong here. So maybe we have been sitting on a very nice algorithm for 10 years, but we don't know it yet. Okay. So let me finish and take 5 more minutes, please, to describe the swap Monte Carlo algorithm, which is an algorithm on which we have been sitting for more than 20 years. Okay, so it's again, so it's a 2-particle move now. So that's a move that involves only 2 particles. So it's the simplest generalization of the 1-particle move. And it goes like this. So again, you take your dense system. It's made of a binary mixture of spheres or continuous polydispersity. So the idea of the swap move is to take 2 particles now at random. Okay, so you take 2 particles. And then you try to swap their positions. And then you accept and reject according to the previous rule as before. So really, you're really trying to do this. And that's it. Okay? So if these 2 particles have different diameters, it's equivalent to saying that you're really not changing the position of the particle, but you're really swapping their diameters. If the particles differ by their size. Okay? So if you have a monocomponent system and you take 2 identical particles and you exchange their position, you've done nothing. So the only way to do something is if you have non-identical particles and then you exchange their positions, equivalently their diameters. Yes? Yeah. Sorry. Then you accept, reject. As usual with Metropolis, for instance, whatever transition rate that follows a detailed balance.
When you choose particle or 2 harmonic movement, there is a way to
at random.
go sequentially through the sample.
I just pick pairs at random completely because then I'm sure that it satisfies reversibility directly.
You just go and pick the same pair until you pick everybody once?
No. I just pick pairs at random. That's it. No other rules.
But that means the initial choice of the positions is kind of optimal.
Say that again?
That means your initial choice of the center of the spheres is optimal.
What do you mean by initial?
Because even if you generate it in random, but maybe
No.
like in the previous Monte Carlo, you can move them.
So just imagine that you have done a long simulations, and then you have these blue spheres are just one typical equilibrium configuration that you've reached. And I'm saying if you do that move and you respect detailed balance, you will reach another equilibrium configuration. So initial conditions, I don't care, because then I will sample many, many configurations. The system is ergodic.
Relax the position at the center of the sphere.
Oh, sorry. Okay. So that's a swap move. Okay. Sorry, I didn't understand the question. So now if you want to set up your Monte Carlo simulations, you will do alternatively translational moves as before and swap moves. Sorry, yes. And then you mix normal MC and swap moves. Otherwise, the particles never move, and that was your question. Sorry, I didn't get it. Okay, so the acceleration for this algorithm, well, we don't know how much it can reach, but it's big. And when I say big, it's really big. We don't know. That's the thing. So to just convince you how big it is, I will sketch a plot, and that will finish the lecture for today. Okay, so if we measure some kind of relaxation time in the simulation, and we use the Arrhenius representation that Gilles has been using all along, and we say divide this by some time scale for the beginning of the slow dynamics, such that when the glassy dynamic is reached, it's about 1 here, or 10 to the 0 if you wish, if you have a log scale. So if you do an ordinary simulation, you'll find something like this. You know, and at the end of the simulations, you'll be limited by your computer time, and this is something like 10 to the 5. So you'll have 5 orders of magnitude at best of dynamics slowing down. So we say that typical experiments are done for a time scale that is something like 10 to the 12. So the experimental glass transition, it's reached when this green line will be reaching 10 to the 12 in these units of the onslaught of slow dynamics. So this is, if you wish, the 7 decades of the 7 orders of magnitude gap between simulations and experiments. So we can, try to extrapolate as best as we can this green line and estimate roughly where PG would be for our models. And this is the blue box that you've seen before in the figure I showed you at the beginning of the lecture. So this is our best estimate for the experimental glass transition. Now we introduce the swap Monte Carlo moves, and for some of the systems that we have been able to study, this is what we find. We find that the relaxation time of those systems at the experimental glass transition is something like 10 to the 2, 10 to the 3. Okay? So while the ordinary dynamics takes 10 to the 12 to summarize the system, with the Monte Carlo swap, you take 2 orders of magnitude only. Okay? And then eventually the algorithm becomes slow again, and this is where we stop our simulations. Okay, so this is with swap. And this is the normal dynamics, or the physical dynamics, if you wish. Okay? So it means that if you wanted to estimate the acceleration factor for this very last simulation that we can do with the swap, when we reach the time limit of the simulation, we would have to extrapolate this to 10 to the 12, and even beyond this 10 to the 12, these 12 orders of magnitude. So we've played this game, but it's giving us stupidly large numbers, so I don't want to give them to you today. But it means that in principle, these simulations correspond to physical times that are really extremely far even from the experimental glass transition. So that's good and bad. And this is how I want to end the lecture for today. So it's good, we're very excited because we have an algorithm that essentially closes the gap with experimental conditions and even goes beyond. So that's why I keep challenging Mark Ediger with his ultra-stable glasses that are supposedly better thermalized than ordinary experiments. So we say now we are competing between ourselves in a friendly way, I would say. So we have simulations that can compare to nice experiments or even ordinary experiments. So that's really cool. We are extremely excited about that. in the corner of our heads, we also have this very bad idea that if you think, 5 minutes about how difficult the algorithm is, just taking two particles and exchanging their positions or their diameter, it's stupid. Okay, so Giulio said, well, if we want to go from one state to another, we would have to know the positions of all the particles in state alpha, the position of all the particles in state beta, change all the particles in a complicated collective way. And this is only the way we would be able to cross these very large barriers between states. And if you think of the physics this way, and this is how we have thought about it for all these years, this should not work at all. Because you're not choosing all the particles and rearranging them in a very clever way. You do something stupid and local that involves two particles. So the bad thing we have behind this is that maybe what we have thought about what's the physics of the glass transition was wrong all along. And the physics may be so much simpler than what we had imagined, and very different from the mean field picture that Giulio has described in the lectures. So maybe, it's not sorted out yet, and we are thinking hard about this, but there is this thing that maybe the physics behind the glass transition here, it was so much simpler than what we had thought all these years. And the swap algorithm is then opening this window on, we have these configurations. It's very nice from the empirical point of view. But on the other hand, it's questioning our approach of the glass transition in a very deep way. And this is what we are doing right now. Thank you.